In this experiment, which is the second of your two gravimetric analysis, you're going to work out the percentage by mass of nickel in a sample of hydrated nickel chloride. In this experiment, you'll measure out a known mass of hydrated nickel chloride, which has the formula NiCl2 6H2O. You then dissolve it in acid, and then you add some of the ligand dimethylglyoxime to it. Dimethylglyoxime is a bidentate ligand in alkaline conditions, and 2 moles of dimethylglyoxime will bond to 1 mole of nickel ions, forming this tetrahedral complex with a coordination number of 4. But remember, you've got 2 different glyoximate ions here. We've got one there and one there, each one being bidentate. Now, the important thing about this complex in this experiment is that it's insoluble in aqueous environments. So the nickel dimethylglyoximate will form a red precipitate, which you can then filter off, dry, weigh, and then once you know the mass of the complex, you can work out the number of moles of the complex, hence the number of moles of nickel, and hence the mass of nickel that you started off with. You will then compare your experimental result with the theoretical value you would expect, and then you need to try and account for any differences between the two sets of results. Okay, first thing we're going to do is weigh out accurately about 0.5 grams of the hydrated nickel chloride. We're going to weigh it straight into a 400ml beaker. So we'll put the beaker on the balance, zero it, and now we're going to add about 0.5 grams. Okay, that's 0.54 grams. So record the mass of hydrated nickel chloride, and then what we want to do is add 20 cubic centimetres of distilled water and stir it until it's all dissolved. So that's it all now dissolved. Of course, this is a quantitative analysis, so we want to make sure we don't remove any of the nickel chloride solution in our glass rod. So let's wash down our glass rod. Okay. Right. So now we add 20 cubic centimetres of 2 molar hydrochloric acid. And then dilute the mixture with deionized water to about 200 cubic centimetres. We just use the markings on the side of the beaker. It just has to be approximately 200. Okay, and now we have to heat the solution to 70 to 80 degrees on a hot plate. So we'll put it on a hot plate and we'll turn it up. I'm going to turn it up to about the maximum temperature just for a wee while to get up to about 50, then I'll turn it down a bit. So I'll just get a thermometer, put it in, and I'll just leave it at maximum until we get to about 50 degrees, then I'll start to turn it down a wee bit just to get it to settle in between 70 or 80. Okay, so that's at around about 50 at the moment, so I'm just going to turn down the heat so it starts to go up a bit more slowly now. Okay. Right, so we've got a temperature now in between 70 or 80 degrees, so we'll turn off the hot plate, take the thermometer out, and in fact, to stop losing some of our nickel, we'll wash down the thermometer when we take it out. And the next instruction is to add 50 cubic centimetres of the dimethylglyoxime. Okay, so let's add that. So that's the ligand which is going to form a complex with the nickel, but it will only happen in an alkaline solution. So we're now going to add some ammonia. The instructions say add 2 mole per litre ammonia solution dropwise and with constant stirring until a permanent red precipitate is obtained. And it says you should add about 30 cubic centimetres of ammonia solution. So I've measured out 30 cubic centimetres of ammonia solution here, and I'm going to start adding it, maybe not quite dropwise, since it would take an awful long time to add 30 cubic centimetres dropwise. So I'm adding squishes. And did you see that red colour appear? Watch for it again. That's the colour of the nickel digloximate complex we're looking for. Eventually we should get a permanent red precipitate, one that stays. In reality, when doing this experiment, I found that I had to add a lot more than 30 cubic centimetres of the ammonia solution. It was probably near 100 mils that I added before we got the permanent red precipitate. The solution should look quite lumpy and a very obvious solid present in it. Then when you have that, you should add an extra 5 cubic centimetres of the ammonia solution just to make sure. And before you take out the thermometer, make sure you wash it down with distilled water so you don't have any transfer losses, losing any of your complex on the thermometer. Then remove it from the hot plate and leave it to cool down for half an hour. Okay. Right, so we've left the sample now to cool down for, well, it says half an hour, probably left it a bit more than that. But as you see, this seems to happen most times. The whole precipitate doesn't fall down to the bottom. Some of it does, but some of it stays at the top. But you've got this clear liquid in the middle. So what we want to do is to test whether or not there's still some nickel ions in that area. So what I'm going to do is insert the pipette into this clear area in the middle and add some more of the ammonia solution. I'm then going to add a pipette of the dimethylglyoxime into the middle area again and see if some more precipitate appears. I don't think any more did appear there. We were just disturbing the precipitate that was already produced. So that tells us that our original precipitate included all the nickel ions. If there had been any nickel ions left in that clear area, we'd have seen more red precipitate being produced. And if that had happened, we'd have added more of the ammonium hydroxide and dimethylglyoxime. But there was no more, so that's fine. Right, we're going to filter precipitate using this thing which is called a Buchner funnel. So what we want to do is have the accurate mass of the Buchner funnel plus the filter paper before we filter it and after we filter it. So we tear the balance, put the Buchner funnel gently on. Need to be a wee bit careful to stop it rolling off. So that's 88.26. So record that on the sheet. The sheet says mass of crucible, it really should say mass of Buchner funnel. That's just a wee mistake. Okay, right, now what we want to do is to filter off the precipitate into the Buchner flask and the Buchner funnel. We use this because just doing a normal filtration the way you did in National 5 or higher would take a very long time. So this time we're going to use a bit of a water pump to produce a vacuum. Okay, so this is a water pump. In this part here you've got a thick pipe up here and a thin pipe here. The thick pipe is what gets attached to the tap. And as the water flows through here, it produces a vacuum here which you attach to this Buchner flask. So let's set this up. So put this on quite tightly. Okay. Make sure the bottom of it's in the sink and attach the side arm to the Buchner flask. Okay. Then put the Buchner funnel with the filter paper in there. Turn the tap on. And if you press this down gently, you'll feel the vacuum pulling the solution through. The more you turn on the tap, the stronger a vacuum you'll get. If you turn the tap on too much, this pipe will come off and soak you. That almost inevitably will happen. Okay, so let's start filtering it. So apply a bit of downward pressure to keep a good vacuum and pour it in. Okay. This might take 10-15 minutes to do. So the red precipitate will be stopped in the Buchner funnel, just keep on topping it up. And keep on filtering. You can try turning up the tap, but again be careful because if you turn it up too much it will come off. But it won't ruin the experiment if that happens, so just play with it. I'll pull this in. Right, I've just stopped the filtration just now because I'm not going to be able to get all this solution into this flask before it's full up. So I've turned the tap off and removed the funnel, and then we're not interested in what's in here, so we can just pour that away. Put it back on, turn the tap on, and then continue filtering. Okay, we've now put all the precipitate, or at least most of the precipitate, into the Buchner funnel, but as you can see there's still quite a lot left on the sides of the flask. So we'll wash down the sides of the flask to try and transfer as much as possible. So I'll do this 2 or 3 times. To try and transfer as much as possible of the red precipitate into the Buchner flask. The chances are you will leave a little bit behind. You can see some markings down the outside of the flask where some of the precipitate has been lost. So this to some extent will account for the fact that you will not get perfect results, because in gravimetric analysis you very often get these transfer losses. Some of the precipitate is left behind. So we'll just leave that to finish filtering. It's nearly done. And then what we want to do, there's no point weighing it now because precipitate is still very wet. So we're going to transfer it to an oven to dry it before weighing it. Okay. The sample's been in the oven for about an hour now at 100 degrees, so we want to take it out and weigh it. But of course we can't weigh it while it's still so hot, so we have to let it cool down in a desiccator before we can weigh it. So it'll be very hot, so make sure you have a glove. Okay. So put the sample in the desiccator. Put the desiccator on and leave it to cool down for maybe about 10 minutes. Okay, the sample's cooled down now, so what I want to do is weigh the sample. So make sure the balance is zeroed. Put the funnel on and get the reading. So it's about 90.35. Okay, so I record that here, 90.35. Of course, we may not have got rid of all the water from the sample yet, so we're going to keep on repeating that heating, cooling the desiccator and re-weighing cycle until we get two results within 0.01 gram of each other. So until we achieve a constant mass, which tells us that all the water has been driven off from the sample. My second weighing gave a mass of 89.06, my third 88.90, my fourth 88.90. So 3 and 4 are within 0.01 of each other, so that is defined as the sample being dried to constant mass. So the mass of nickel to dimethylglyoxime is the average of these two values, which is 88.9. Take away the original value for the mass of the book in a funnel and filter paper. So 88.90 minus 88.26 means that the mass of the nickel dimethylglyoxime complex is 0.64 grams. Over the page, you're then asked to determine the percentage of mass by mass of nickel in your sample of hydrated nickel chloride using these results. To do that, the first thing you have to do is work out the number of moles you've got of nickel dimethylglyoxime. Then we'll calculate the number of moles of nickel 2 plus ions, which will be the same because there's 1 mole of nickel 2 plus ions and 1 mole of nickel dimethylglyoxime. So thereafter work out the mass of nickel ions in your complex and hence the percentage of nickel in your original sample. Then compare that value with the theoretical percentage worked out using this formula for the hydrated nickel chloride. And in the discussion you've got to first of all offer up reasons for any difference that there might be between the experimental and theoretical values, and then finally explain how you checked that there was no more nickel ions remaining in the solution after the initial precipitation.